Everybody, Taylor Sparks back with our Materials Informatics series, and today we're talking about Bayesian optimization, probably the most well-known and certainly the most important application of Bayes' theorem to materials research, because it allows us to incrementally improve something, which is something that we're already trying to do in material science. Now, let me start by saying that there is a ton to say about Bayesian optimization, and in today's brief video, it's just a brief introduction. And if you want to learn more, we have this playlist. So check it out. We cover a ton of stuff from, comparing Bayesian with other approaches, how do you do this in closed loop, how do you do ML model tuning, on and on and on. How do you do this in batches? What if you have asynchronous versus synchronous, workers doing the optimization? There's just a lot there. My student Sterling put together these videos and we released them over Christmas a few years ago, and they're fantastic. But today we're going to get just to the fundamentals. And maybe the first question to ask is, well, why? Well, I would say that if you're studying material science, then you already know that materials design is filled with difficult property trade-off situations, right? With metals, do you prioritize strength or ductility? It's hard to have both. What about if you're 3D printing something? Anybody used a 3D printer? We're going to show you an example in a moment. But getting those print parameters set correctly is not trivial. What about in plastics when we're looking at performance versus, say, biodegradability or recyclability? Those things don't typically come one with another. You have to have the trade-off there. What about in catalysis? Now you're looking at activity versus selectivity maybe. Or thermal versus electrical transport. Devices like thermoelectrics, you can't just have both of those maximized. You have to have one or the other, so there's a trade-off. Or in thermal barrier coatings, maybe it's a mechanical strength and a thermal properties that you're trying to trade off. On and on and on. Most applications, in fact, no application relies on a single parameter because there's always at least cost plus some sort of material property. So how do you optimize as you develop new materials or select amongst known materials? How do you do that optimization? Well, one way to do it is with Bayesian optimization. And let's just give an example. Let's go back to our 3D printer example. Imagine you work at a company and your boss says, hey, there's maybe something to this 3D printing business. We should start doing this. And so a custom, request came in from a client and your boss says, okay, you've got a week to get our new machine dialed in. And then we want you to print that customer's part. Well, you might ask then, what's the most efficient way to go about doing that? Because you've got all these different print parameters, right? If anybody's printed, you know that you've got your X offset, your Y offset, there's the prime delay, there's the print speed. Even if you just consider those four, how do you explore the right combination of those four? And what values do you use? Let's assume a really naive situation where you only are going to use low and high values for those, right? So you just got two different settings, low versus high for X, Y, and those different things, right? Well, one way to do this would be to set up a design of experiment. This is what most engineering students are familiar with when they show up in college, has been my experience. They're familiar with the idea of a design of experiment. You've got a bunch of parameters. Okay, so hold everything constant. Those variables get held constant. You change one variable and you look at its performance. And then you do that for the next one and the next one, right? So obviously this grid of possible interactions between all the experiments becomes really big, really fast. Just the one that we've talked about, right? Assuming that you're going to do 3 replicates because we believe in measuring uncertainty and repeatability. So you've got 3 replicates. You have just 2 levels, high and low, with 4 different variables. All of a sudden you're talking about 48 experiments, right? And really that's just getting started, because your notion that like, oh, we can just do like a high and a low setting on all of our different parameters. What if the true optimum performance, which is most likely the case when you look at real data, what if the optimum is not just high or low, but rather somewhere in between? Look at this real scenario. This is actual data from 3D printing, right? If you look at it, there's noise here. There is definitely like a nonlinear curve here. So this is a trend that is going to be difficult to learn if you tried to rely on design of experiments. It's going to be too slow, too complicated to do that. So we need a better approach, right? This is where optimization, comes in. The whole idea, like the formulation, the approach behind optimization is that there exists some objective function, we'll call it F. Like this is like, if I look at this real data, like there's some curve, right, that fits this real data, right? That's your objective function, right? Which ideally, if you had like infinite data, you would know what that function surface looks like. And then you have your domain over which you can explore, right, your different settings. That's going to be our X domain. That's the domain over which the function operates. So optimization is simply, we're going to systematically search over the entire domain of potential, parameter values, which one gives us, in this case, the global maximum value of our function, or minimum, right? It's very often written as a maximum, but it could be a minimum, or it could be a specific value. Maybe you don't want just have like a really high band gap or a zero band gap. You want like a very specific band gap, right? You could set it up that way as well. But it's that idea of, oh, there exists some function and there are solutions to that function, right? But how do you know which one, right? So technically, you don't even need to know the function in order to find the optima, right? So let's say the actual function, who knows, what that equation is. You don't know it. But what you could do is you could set up this sort of test scenario where here's what you're going to do. You're going to initialize some data set, so you've got some data points, right? And that can even be empty if you want to start with. And then you're going to have a policy and observation, and then you're going to have that added to your data set. So the policy says, go out and select some observation data point. Maybe you've got a rule that is telling you how to do that. Maybe just picking randomly, right? But you have some sort of policy that tells you, okay, collect a new data point. You then collect that data point, that's your observation, and you add that to your data set, and then you update your data set. So you could do that straight up randomly until you reach some criteria that is satisfactory, right? Maybe you've got like that green dashed line represents your target threshold. As soon as you get a parameter of your print settings, for example, that's better than that, it's good enough. And at that point, you could just stop. Or maybe you stop when you run out of time, or your budget for experiments gets, run out. You run out of cost or available material, or who knows what else. But the idea here is that you could, if you wanted to, just keep on sampling directly without ever trying to learn the underlying function. You just keep trying things randomly. Now, obviously, that's not going to be the best way to do that, but that is one approach. And there's a couple of reasons why it's not great. First off, it's very inefficient because if you're learning, like if you look at the actual data points, it's clear that as you're increasing over here that the data points are sort of falling off. So if you're trying to increase something, it's less likely that you're going to get a good hit, and it's more likely that it's going to continue to go down. Another problem is, what about measurement noise? Like this single data point, if you assume that there's actually now noise in your measurement, is that really above the threshold, or was that just a single measurement and that's noise, right? That becomes tricky. So you don't want to rely on an overly simple observational model. It would be better to try and learn what the underlying form of the objective function is. So how do you do that? That's where surrogate models become really helpful. Now, surrogate models, I get it. First off, the surrogate model is wrong, but it's still useful, right? If you look at the dashed blue line, that's our objective function, which we don't know, right? But if you collected 1 million data points, you might learn that that's what the function is. Well, if you've only got 5 or 6 data points and you try and fit a surrogate model to it, which is sort of a proxy for the actual objective function, it may not get it right everywhere, but look at all the places where it does get it right. And even better, what if it's a surrogate model that is pretty easy to update so that when you get a new data point, you learn like, oh shoot, it actually didn't do this. There was another maximum, a local maximum to be found over here, right? That would be a really great approach, right? So that's the idea behind Bayesian optimization, is that, okay, let's just go ahead and improve our understanding of how the surrogate model is fitting the objective function by iteratively collecting new data. And maybe you have a really bad model at first. Like here, they're just putting like, maybe it's set to 0 or some average value, right? And then when you get a couple data points, you start to fit like a really clumsy surrogate model, which gets it wrong a lot. But as you add more and more data, you start to see that your belief about the form changes with more observations, and we're able to more accurately learn the underlying objective function, right? So you hear me talking about things like we're learning over time. You had an idea and then you updated it. That pairs really well with our previous videos you saw where we talked about Bayes' theorem, naive Bayes, Gaussian processes, which is exactly the same idea, right? In all of those videos, we were talking about this notion that in Bayes' theorem, you are trying to calculate a posterior distribution, right? What is the distribution of phi having some observed values of x and y, right? And you're going to do that by using priors, right? Which is what do we believe about phi before observing data, and some likelihood, which is where phi is most compatible with some observations y that we have, right? So using this, by the way, I think this is easier to see sort of graphically or visually. If this was our prior assumption, right, this is what we've seen previously with data, but then you've got some likelihood based off of conditional probabilities where you think actually the likelihood is actually over here, then the posterior, since it's the product of those, would look like this new curve there. And as you add more data, you update your likelihoods, you update your posteriors become your priors then can calculate new posteriors, and you can iteratively get better and better. Okay? And obviously, uncertainty changes the way that we approach this decision-making process. Consider for a moment two materials, A and B, and they've got two different strength values. So B is stronger than A. So which material would you use if you're going to build something that's really important, like an elevator shaft or a bridge support or some component in a vehicle? Lives could be lost if it fails. You're probably thinking, well, use B. Why would you ever use A? Unless it's crazy more expensive or something, or there's other materials properties that are bad. But all things equal, B is better than A, right? What if we consider uncertainty, the variability in that, right? Now you know that it sort of has this distribution where, forgive the clunky PowerPoint art here, but if B was a distribution called a normal distribution that had a broader distribution, a higher standard deviation, even though the mean, the average, was higher than A, if A has a really tight distribution, then I think what we're worried about is actually catastrophic failure coming from really low strength failures, right? So in this case, it would actually, my assumption is I would rather design with a slightly weaker material that's more reliable because it has a tighter distribution. So I would select A over B, right? Well, it's the same with Gaussian process and other Bayesian optimization approaches. We care about making predictions, but we want to do it in the context of uncertainty. And Gaussian processes, which we covered in our last video, go back and check it out, are really great because they are flexible, probabilistic surrogate models that provide not only a prediction, an average, right? The posterior mean, that's the blue line, right? Here's our prior, then we actually collected a couple data points. You see the blue line in the center here, that's our now posterior mean. That's what it thinks the average response is. But you've also got these windows of our posterior credible interval, right? That could be one standard deviation from the mean. It could be two standard deviations. It's whatever you chose. If it's 95%, I think that's two standard deviations, right? So all of a sudden, we have a way of predicting not only the predicted performance, but what's our uncertainty there. So with that uncertainty, we can now do lots of cool things for selecting our next data point. Well, maybe just ask yourself, like, if you were trying to maximize this value on the y-axis here, whatever that value represents, strength or whatever else, and you have three data points, right? You've got three observations to go from. Where would you choose your next data point? You've got big bands of uncertainty, right? But you've got some points that were like, here was your highest point, here was your lowest. So what would you choose next if you were going to try and find the next data point, given that your surrogate models are right now quite uncertain? You haven't learned the objective function form or the solution yet. Well, you've got options. And really, optimization is about exploring these different options in a systematic way. And one classic scenario is to balance the need for exploration with the need for exploitation. So what do I mean by that? Well, the regions of your surrogate model where the uncertainty is large have benefit of being something that you could explore. Like maybe the model is going to be way off, and because it's a high uncertainty here, maybe the next data point is huge over here, right? There's lots of uncertainty after all. But on the other hand, there's exploitation, which is exploiting what you already know about the system from previous samples. This guy right here, that was a really high data point, right? The average is predicted to be high. The uncertainty is a little bit less, right? The uncertainty is lower, but it's higher. So oftentimes in optimization, we're going to try and balance a little bit of exploitation, like pick good values that were already high or low or whatever we're asking it to do, but then balance that with ones that have high potential for being even better because they have high uncertainty, okay? So the way that we do that is by using an acquisition function. An acquisition function is simply a guide that tells us what to do next. If we take that exact same Gaussian process surrogate function with just three data points and the associated uncertainties, an acquisition function could actually calculate regions that take into account both the average value and the uncertainty, or just the uncertainty, right? There's different acquisition functions that we could use. But let's say whatever this acquisition function is here, it tells you that that spot is actually now your best new spot to try and sample a data point. So if you're going to go back to the laboratory, if you have all the different design space to choose from, you now have a reason to choose that over the others. Then it's going to be based off of probability and statistics, so it's more likely to be successful than just picking at random. Much more likely. Okay? So which acquisition function do you use? There's a couple that are worth mentioning for sure, like upper confidence bound is one. upper confidence bound is just written out as this. The solution for this upper confidence band is simply equal to a mean plus some uncertainty that gets scaled by some parameter, right? There's sigma equals 1 and sigma equals 2. The same form of the solution, but one, it allows you to scale it. How much do you care about uncertainty? A little bit or a lot? You have this scaling parameter. Another really popular one is expected improvement. Expected improvement, the equation looks like this. You've got some mean minus your function, right? You've got terms representing your mean over here and your uncertainty over there. So you're adding contributions from both of those. And we could go on. There's lots and lots of different acquisition functions. They're sort of like opinions, right? There's tons. Probability improvement, knowledge gradient, mutual information, Thompson sampling, entropy, max value entropy. It could go on. And there's not like one that you should always use. I find myself very often using expected improvement. The literature certainly uses that a lot, but there's no reason to believe that it's the very best. And you can try different ones. But what you want this function to be is relatively inexpensive to calculate, because again, you're going to calculate it for all the values along the x there. You want to calculate it for all potential solutions. And if it's a really slow thing to calculate, that's not going to be useful. Bayesian optimization, you want to be able to evaluate all the different potential ones very quickly with some surrogate, right? It's not your surrogate model, but some quick measure of worthness in calculating that next data point or going out and experimentally measuring it, okay? Another thing to think about when it comes to Bayesian optimization, you have your surrogate model choice, and we've showed you Gaussian processes, but you can do many others, right? You could do random forest or sport vector machines, all the things that we've learned about previously, all the different models that are out there. Any of those can be used for a Bayesian optimization. Now, if you're doing expected improvement that requires you to account for uncertainty, you're going to have to figure out how to get uncertainty from those models, which is not built in. So you have to do things like bootstrapping. If we go back to our video on ensemble methods, we talked about bootstrapping as a way to get uncertainty. But in any case, you've got to have some sort of surrogate model. You have to have some sort of acquisition function, and you have to have some data to start with. And the data that you start with is actually pretty critical. It changes pretty dramatically how quickly your active learning campaign, your Bayesian optimization campaign, can converge to some optimum scenario where you've met your final, right? So for example, you could consider by starting with a grid search. That's sort of like the design of experiment we mentioned earlier. Or maybe you're like, no, I'm just going to pick points at random. You could do that. Actually, there's something even better than grid or random, and that's using these so-called quasi-random sequences. And there's several to pick from. There's Sobel, there's Halton, Hammersley, Latin hypercube. There's different ones. And I find that those are actually pretty good starting points. That we use those. We use Latin hypercube for most of the times when I'm generating my starting data. And how much data do you start with versus how much do you turn it loose to generate? You know, is totally a judgment call that you're making. It's a hyperparameter in the process. Do you start with a dozen data points, or do you wait till you have a couple dozen? Do you start with even fewer, right? These are options that you have. But, you know, we typically start with at least 10 data points, either randomly or Latin hypercube quasi-randomly selected from the design space. And then we turn it over to the Bayesian optimization, letting it drive and tell us where to look next, okay? By the way, more on these different, you know, grid versus random versus quasi-random versus Bayesian in this videos that follow that Sterling put together. So check out the link below. Okay, let's pause for a moment and make sure that you understand all the different key blocks that go into Bayesian optimization. So first off, you have to have some sort of generation strategy for your initial data, whether that's random, quasi-random, whatever it is, some strategy for selecting data, and then you come up with that data, and now you've got a data pool. Sweet. Once you've got a data pool, now you can fit a model to that data pool, some sort of surrogate model, Gaussian process, random forest, many different options here, right? Using that surrogate model, we're going to train the model on the data and then use that model and an acquisition function to calculate which experiment should come next. We then go out and we do an experimental observation, which is going to allow us to add data to our data pool, right? And you periodically ask yourself, have we met our termination criteria? Have we met a material that is strong enough or has a specific, you know, materials property that we're looking for? If no, then keep on going until your budget runs out. And if yes, then you're finished, right? That is essentially the workflow of Bayesian optimization, okay? Now, it gets complicated. I imagine you could see really quickly how this can get harder. Like, what if you care about more than just a single property, which is always the case, right? What if it's not just strength, but it's also cost? You want to maximize one, minimize the other, right? The highest strength material is probably really expensive. The cheapest material is probably really weak. It's a common scenario. So what is optimal? Or in other words, how much are you willing to spend for an increase in strength? These become a little bit hard, right? So what do you do about that? Well, the simplest way to deal with it is what's called scalarization, right? We're going to make a scalar, a single value, some sort of score that takes into account multiple different objectives, right? So the overall score might be equal to some lambda, some weighing parameter, like it tells us how much we care about strength score, plus 1 minus that value for the cost score, right? So this would be one way to do it. This allows us to come up with a new score. And obviously this function could be as simple or as complex as you want. This is a really simple one that I'm showing you. So what are the strengths and weaknesses of this? It will give you a single value, which is nice at the end. But the downside is that you had to select that value of lambda. So how much importance do you put on strength versus cost? That's a bit subjective, and it would depend. Some projects, it might be worth it to pay the extra money for high strength, but others you might actually want to prioritize lower cost. And so really there's a full trade-off, and picking a single value doesn't let you explore that full trade-off. It just picks a single one sort of naively. So that's not great. So there's a better way to do this, and that's with this notion of what's called a Parado front. The Parado front gives you the line of maximum trade-off. So here we've got axes for strength, which we're trying to maximize, and cost, which we're trying to minimize. Therefore, these purple solutions are the ones that are the so-called non-dominated solutions. They are the ones where you can't get better among your known solutions. You've got other known solutions which are dominated, where like this one right here, well, technically there's a better solution available. There is something with higher strength and lower cost. That is a better solution. It's a dominant, so therefore this is a dominated solution. And the other ones exist along the Pareto front. And now with this, you can see, look, you got like 9 or 10 different materials which explore sort of fully the trade-off between the two different properties that you might care about, which is going to help you make more informed decisions as an engineer, okay? And obviously this could be extended to not just 2 dimensions, but n dimensions. But now you're looking at regions that capture the largest hypervolume. You're trying to maximize the hypervolume, which is some region in higher dimensional space. But it's the same exact approach. It extends really nicely, okay? So briefly, I'll just show you one cool example from the literature on this. This comes from a paper in 2018 by Yuan et al. In Advanced Materials, where they were trying to find new piezoelectric materials based off of barium titanate. They're trying to get a really high electrostrain. So when you apply a voltage to it, right, it's how much strain is induced in the piezoelectric. They built a data set, right? They have a data set that only had 50 data points. That is not a lot of data points, right? You're not going to hit this with like a machine, a neural network or something. It's just not enough data. With only 50 data points, and then once they've got those 50 training points, they're going to use a Bayesian model to do 5 iterations of adaptive design, where they're going to explore the trade-offs possible, and they're going to look at, what to do based off of exploration, exploitation, or some combination, right? And then compare that with random selection. And here's what they find. So again, these points on the far left represent iteration 0. That's the training data set. That's the 50 data points that they had to start with. And the best thing they had a highest measured strain, electrostrain of like 0.15, right? Okay. And then they did 5 iterations. In one case, they just picked randomly. So that's the purple ones. And it's sort of, you never saw anything better than what they'd seen before. Bummer. In another one, they prioritized exploration, which was, they got 1 out of the 5 that was better because they were just picking, not totally randomly, because they were picking in regions of high uncertainty, which is not the same thing as picking randomly. They did one which was exploitation, which kind of did the same, but a little bit better. And one where they used probably something like expected improvement, I have to check the paper, where they see a trade-off between exploitation, exploration, and they do really well. They find 5 materials that all outperform the 50 that they started from. Results like this are very common to find in the material science literature now. Bayesian optimization is a really powerful tool as you are going to be iteratively going to the lab. It works well with small amounts of data. It works really well with the notion that you don't have a lot of data to start with, but you do have the ability to query the oracle, right? Collect new data in the lab and improve over time. It works well when you have clearly defined objectives that you want to maximize or minimize. It does have some challenges, and the biggest one is feature space. Just like with Gaussian process, like we showed you in the last video, as you move towards many, many features, it sort of collapses. It becomes really problematic. So your ability to do feature reduction becomes pretty important. So you might be asking, how do I go about implementing these things? This sounds cool. Well, good news is also that there's so many tools available. There's AXE, Adaptive Experimentation Platform. That's by Meta. We use that all the time. We love it. There's Blowtorch, there's Dragonfly, there's Baby. These different things have pros and cons. I haven't used all of them. We use Blowtorch and AXE quite a bit. I have not used Dragonfly, although my student has and he likes it. And I've got another group of students who have used Baby and they like it a lot. But there's a bunch. Or you could do it by hand. In fact, in our next video, we're just going to code a basic Bayesian optimization using expected improvement by hand and show you that it's really not so bad. Okay, one last plug for my amazing former student, Sterling Baird, who put together an awesome series on Bayesian optimization. The videos are pretty short, 5, 10, 15, 20 minutes. And they cover all sorts of stuff, like how do you do this if you're doing multiple objectives? How do you do it if you have continuous multi-fidelity optimization? Right? So now you've got different ways to experiment. Like maybe you've got like the full tensile test and hardness. How do you take those two different fidelity of data and combine it in some sort of optimization campaign? There's discrete versus continuous. There's offline optimization. There's batch optimization, asynchronous, on and on and on. I think it's a really great series, so check it out, link below. And with that, let's pivot and talk about large language models in materials. Okay, see you next time.